Pamu sir?
Yeah, tell me.
Yes, sir. We could listen your voice and we could see your screen, sir, perfectly.
Okay, thank you.
You can come to presenter mode, sir. You can just press F5 of that button so that the full screen will come.
I have
Good morning, sir.
mode.
Are you able to hear me, sir?
Yeah.
Shanita, I could able to hear you clearly, no problem.
Okay, sir.
Shanita, one thing I want to let you know, once you had an introduction, immediately mute. There is echo is coming from your laptop, I guess. Once you mute, I think it is clear.
Okay, sir, I will.
Yeah, thank you. Thank you.
Over to Pamu, over to Dr. Pamu. Dr. Pamu, sir, can you speak once?
Yeah, good morning all. Am I
Yes, sir, perfect, sir. Sir, it is perfect, sir.
but I hear a lot of noise.
Yeah, now, Shanita, could you mute yourself? Yeah. Now, sir?
It's fine, yeah.
Okay, sir. So now at 9:55, Shanita will start introducing you. So it may take 2-3 minutes. And after that, it will be over to you, sir. It will be till 11:30 a.m., sir. Okay, sir?
No problem.
And
Thank you.
the questions will be posted by the participants in the right-hand side chat box. You need not worry, sir. Shanita will once again ask you after the talk, sir. Maybe I advise you by 11:25, you can complete the talk and the 5 minutes discussion will be there, sir.
No problem.
Yeah, thank you very much, sir. And my dear participants, very good morning to one and all. I assume number of participants are very less, but however, as per the feedback of the first session from Professor C.H. Subramaniam Garu from IIT Hyderabad, I understood that most of the people want to have a talk on facial synthesis of nanomaterials. So if everyone is okay on Friday afternoon 2:30, so that I can arrange one more talk only on facial synthesis of nanomaterials. If you say in your chat box or in your feedback form, you need that session, I can arrange a session, an extra session that is on Friday 28th afternoon 2:30. So please let me know from your feedback. Based on that, it may be in Telegram or it may be in WhatsApp or it may be in the chat box, whatever it might be. So now, within 1 minute, Shanita, you can take over the thing and you can introduce Dr. Pamu sir to the audience. And then you please mute your mic, Shanita.
Sure, sir.
Dr. Pamu sir, could you make your screen large?
Shanita, if you can use your...
Yeah, I am in full screen mode only.
It's a full screen, sir. KVR guide is in full screen, actually.
Yeah, okay, sir.
It's clear, visible. Yeah, Shanita, if you can able to use your headset, I think your the disturbance might get reduced, ma'am. I think you are using a built-in mic of the laptop, I guess.
Yes, sir, I'll get it from tomorrow.
Yeah, that's fine. Yeah, as soon as you introduce, immediately just you mute yourself because it is echo is coming from the audio from your laptop. That's all.
Shanita, you can start introducing Professor Pamu sir.
Good morning, everyone. So I'll introduce Dr. Pamu, sir, who's going to deliver his next talk for our STTP program. Dr. D. Pamu currently is working as an associate professor at Department of Physics, IIT Guwahati. He worked as assistant professor of physics, IIT Guwahati from 2009 March to 2014 July. He has obtained his Dr. D.S. Kothari's postdoctoral fellowship sponsored by UGC at University of Hyderabad between 2008 to 2009. He has done his PhD in physics from University of Hyderabad in 2008. He has worked as a postdoctoral fellow in School of Physics in University of Hyderabad. He also worked as Senior Research Fellow in National Fusion Program project entitled Development of High K and Low Mass Materials for Microwave Windows in Fusion System. He also worked as Junior Research Fellow and Senior Research Fellow in ISRO project entitled Development of High K and Low Loss Materials for Miniaturized Integrated Circuit Applications. He's been awarded as Young Scientist Research from Science and Engineering Research Board, sponsored by Department of Science and Technology in 2012. He is also awarded as Young Scientist Research from Board of Research in Nuclear Sciences, DAE in 2010. He has published 101 publications in international journals and 78 publications in national and international conferences. He has organized Quality Improvement Program, short-term course on smart materials and their applications in nanotechnology in December 2014. Now I request Dr. Pamu sir to start his lecture.
Yeah, a very good morning to all. I thank the organizers for giving me this opportunity, especially
Dr. Pamu, I'm sorry to disturb you. Very sorry.
Yeah.
We will start at exactly 10 a.m. It is 3 more minutes are there. Is it okay to wait exactly at 10 o'clock till 10 o'clock? In the meantime,
No
okay. Thank you.
No problem. No problem.
Thank you. Thank you. We will start now. It is 7:57, 9:57. We will start exactly at 10 a.m. sir. Okay, sir.
No problem. No problem.
Thank you, sir.
Yeah.
My dear participants, once again, one small request from all of you. There is from the feedback from yesterday, Dr. Professor C.H. Subramaniam from IIT Hyderabad. In his feedback, most of the people were asking a facial synthesis of nanomaterials, a total talk on facial synthesis of nanomaterials. So if you once again put it in the chat box, if you require only on synthesis one talk, I can arrange it on 28th, that is Friday afternoon, 2:30 to 4 o'clock, 1.5 hour session. If depending on the participants' request, I can plan that also. And I request all the delegates, please submit your feedback forms as well. Please try to attend all the sessions. We are providing all the information in the Telegram as well as in the WhatsApp groups. However, there is Nano Digest. Once again, one more web link is there, YouTube link is there. That is also live streamed. I am also sharing the YouTube link. Thank you very much. Over to Professor Dr. Pamu, sir.
Yeah. It is just few more seconds in my. So shall I?
Yes, sir. Yes, sir.
Yeah. Oh, very good morning to all, and I thank the organizers for giving me this time to just introduce the synthesis of nanomaterials. Of course, this is the advertisement I am hearing that you people are very much interested in synthesizing the nanomaterials. But I am going to give a brief introduction to thin film technology, where we will be able to fabricate thin films. When we talk about particles, nanoparticles below a critical size, the controllability is difficult, but which is very easy or obvious in the case of thin film deposition. So I will just briefly introduce. Of course, my talk is very vast, but I will try to give a brief information. However, I will share my slides so that if you want to go further details, you can. And if you have any queries even later, you can interact with me. Okay, so let us move on. When we are talking about thin films, what is the importance of thin films? Why we are so much interested about this thin films we will see here? Because if we want to define, let me define a thin film. Like it is a three-dimensional solid where one dimension is much smaller than the other two. So that is called the thickness. So the thin films range can be different. You know, if I talk to an electronics person, for him 100 nanometers is 100 nanometers. Or if I talk to a mechanical engineer, 100 nanometers, what 100 nanometers? So because it depends on the perspective and the application where we are interested in. Where when we talk about CMOS technology, 3 nanometers is good enough for them, whereas a mechanical engineer needs a 3 microns. So it varies from person to persons. Okay, and so let me give a what is the share of nanotechnology or thin films in various industries. I have given you know the various percentages that we are right now employing the thin film technology in the market. So you can see the market, it is overwhelming. Of course, this statistics is about 4 or 5 years old, but
Dr. Pamu garu, small thing. And there is actually some screen is not visible. Can you stop and start your screen sharing, please?
oh, again, okay.
Just stop and share because of that. Yeah, please start again.
Just a second. You are able to see now?
No.
No.
No. So you just you need to reshare.
Just a second. Just a second. Then let me.
Yeah. So because almost 1/3 of the screen was with hidden. Actually, we could not able to see the PPT.
Oh. Okay. Let me. Just a second. Let me close
Yeah,
the
sure.
other applications so that.
You choose only the PPT which you are going to share.
Yeah.
You are sharing your browser. We don't want the browser. Just use your PPT only.
Yes.
Pamu sir, please open your PPT, then share it.
Yeah.
It is already open.
Yeah.
This is my PPT open, and
Yeah.
I
In
am
the share content, click on that. You will have some multiple options of the desktop, browser, and the PPT. You choose only browser, PPT and share on that one.
Yeah, you are able to see now?
Now it seems to be fine. Can you maximize it, please?
Yeah. Is it fine?
Now it's fine. Please go ahead.
Yeah. So
sorry for the interruption, sir.
It's fine. It's fine. Okay. So I am just giving the general statistics, the importance of thin film technology being used in various technologies. So that is where this has gotten a very much importance. I just want to give a generalized applications, and then I will go into the importance of how do we deposit thin films, and then for time permits we will also see how to characterize the thin films. So that the MEMS structures is one of the smart technology that is coming up, and where the device size is much smaller. And in this part, we see that the thin films are very much evident in fabricating all the applications that are shown in the screen. And we know that in every part of electronic device, so whether it is a packaging or it is a smaller size of the devices, which is very much compatible with the semiconductor industry. That is where these thin films are very much used in the technological aspect. And even we know that even layers and all this, in every case we see a thin layer of it. Sometimes you may not directly deposit a film, but you will slice a thin layer of plastic and you are putting up. That is where this is the commercial application of it. And then we will also move on. So aeronautical industry, or whether the turbines or telecommunications, we see that thin film technology is very vital. Why it is vital is that it is very easy to protect the device from the environmental aspects, whereas which is not possible with the most of the other nanotechnological methods, nanomaterial synthesis methods that we use. Okay, so and now we know that even MI started transparent screen TV, where when you switch on TV only, you will see the screen. Otherwise, it is transparent. Why that is happening is that this is again transparent oxides that are being used, and the coatings where you will see the 100% transmittance of the light. And we will see now we are moving on to the flexible devices where again a thin layer of the material that we are interested deposit on the device and we are able to use it effectively. So these are the some of the applications, and we know that various aspects of it is coming. This is one examples of that, and these are also again you can have a MEM structures with different on different flexible substrates, so that it is not rigid, but you will be able to you know uh, tune or bend the device according to your requirement, and which will allow the thin film, because your thickness is so small that it doesn't make any it doesn't distort the structure of the material itself. So that is the advantage that we have. And we also know that solar panels, all that, which is you can make it even lighter so that the entire house can be. And we see in Kerala and all that they built with the solar panels, so that you don't need a extra electricity connections also. So that is what is possible because these solar panels have become very thin because of the thin film technology. So now if you see the market gap, the thin film market gap is very huge in the market because it is tremendously progressing in various technological aspects. And these statistics are a little old. So these statistics are only in 2012. I am unable to get a new one, but you will see that it now from 2012 to now, so it's almost 70% enhancement in the thin film devices in the market and the different electronics uses. This is due to mostly due to the electronic devices such as mobiles or your tablets and other electronic computer devices. So due to that, the thin film technology has gone up so much. So now, so these are the applications. But how do I do thin films? And the in the industry seems to be very promising, but how do I do a thin film? How do I deposit a thin film? What is the method that we follow? That is what we are going to see from now on. So thin films are, we start with a small, thick plate, and from that we will try to slice a thin layers of it and put it onto a substrate wherever I want. So now what we are basically going to do is that, we are going to do a layer by layer, and initially you vaporize it and again condense it onto a substrate. That is what happens in the case of a physical vapor deposition. That anyway I will come to that. So, and as we move on, so you will be able to distinguish between a thin film and thick film. That as I told you, that for somebody thin is very thin, for somebody thick is very thick. So whatever is your need, you have to choose. So now, so why we call thin films is that a thin film film considered as a thin when its properties are significantly different from its bulk. Why it is so? Because of the large surface raised to volume surface to volume ratio is the main thing. That is what probably yesterday also you would have heard when we are talking about a nanotechnology. These aspects will come very evident when we have a thin layer of the material on the surface of the substrate. Of course, this is the general classification of a thin film methods. So you can have a gaseous state and solution state and a molten or a semi-molten state. So in the gaseous state, we have a methods called CVD, that is chemical vapor technology, PVD, physical vapor deposition technology, physical vapor deposition. IBAD is ion beam state deposition. So in this case, what happens is initially you start with the solid and make the vaporize the solid and make then you bring it to the substrate and condense it. That is what is called the gaseous state method. Solution state method means, that Sol-Gel process is one of the best example. That means you make a solution of the material that you want to deposit on a particular surface, and then you dip your substrate, or you put a layer of it and then make. That is called the solution. And molten or semi-molten is a thermal spraying, welding, of course laser welding. All these are all comes under the semi-molten state or molten state techniques. But however, today's my interest will be more on gaseous state, because this is precisely required for various applications. Okay, so I am not underestimating the other this thing, because I am only my focus and my expertise is only on the PVD or the gaseous state methods. However, solution based methods are also equally important when you start working on it. So in this case, what we do is PVD CVD, how you will do is that in the physical vapor deposition, you start with a solid material and then you vaporize it and you will have a thin film. But in the case of CVD, that is chemical vapor deposition, what you will do is you will take materials in the gaseous form or in the volatile form, and then make those materials to react on a substrate, and then you will form a thin film deposition. So that is the basic difference between a PVD and CVD. Of course, I will also enhance further. Let me distinguish. This is the crucial slide, and based on later I will go a bit diverse way. So what are the factors that distinguish PVD and CVD? So reliance on solid or molten sources as opposed to generally gaseous precursors in CVD. So what happens is you will totally depend on the volatile components in the CVD. Physical mechanisms like evaporation, collision, impact by which source atoms enter into the gas phase. That is what happens in the PVD. So a reduced pressure environment through which the gases species are transformed. So this is different from CVD. That's where PVD has a different advantage than the CVD. So now when we are talking about thin film deposition, is a physical characteristics. Like what you are basically doing is a surface are modified by applying the very thin coating, often just a few millions of a millimeter thick or a few angstroms or a few nanometers. Of course, they are used in various applications, as I already discussed to you. So in order to produce such thin films, the deposit must be applied in a very controlled manner. This is what is the important. Sometimes what we need to do is we need to have an atomic monolayer. That means one thin layer of the material that you are expecting. So which needs a clean substrate. For that, again, you need to have a vacuum. That is what. So when I am talking about the PVD, physical vapor deposition methods, vacuum is a must component, because unless you have a vacuum, you will not have a clean surface in the conditions, which will not allow you. Otherwise, you will not have a good qualitative thin film if you don't have a vacuum. But in the case of CVD, of course, why I would have purely focused on PVD today, but CVD, one advantage is that in the case of PVD, you have to have a capital investments. But whereas in the PVD, you don't, CVD, you don't need to have a capital investments. If you can make a minor changes in the quartz tube and some heater inside that, and if you can place your substrate and allow the precursors to go into the quartz tube, you will be able to do the experiments. But whereas PVD requires some initial equipment like a vacuum system, power supply, cathode, all that it is required. So that is where I am giving some more introduction to CVD. So now in the CVD, substrate is exposed. In the CVD, substrate is all the more important one, because the entire reaction takes place only on the substrate. So you will introduce the precursors into the container, and inside the container you will have a substrate. Underneath the substrate you will have the heater. So what happens is when you heat it, the precursors will come to the substrate and they will decompose and form a reaction. That is what happens in the CVD. So it is some kind of a slightly different from a solution based method, but you start with the solutions or gases and finally you end up with a solid in the case of a CVD. So the growth of film is often enhanced either by heating the substrate or by using the plasma. So you can also use the plasma, because sometimes you have to use the plasma enhanced CVD. Maybe I will give a small example of it as we move on. So in some cases, both are used. That means what you will do, you will heat the substrate and have some chemical reaction to happen, or you at the same time you will also use a plasma to break the bonds between the organic molecules that you take inside. In CVD, most of the times you will use the volatile components to reaction to form the reaction. But whereas in the PVD, you will not use any volatile, you will use a solid vapors. So that is the main difference that I am just telling. So when we come to PVD, physical vapor deposition method, so there are few methods. I will just introduce each of them maybe a couple of minutes and explain their principles, which are very general, common methods required for deposition. And similarly, CVD also I do the same thing. Okay, so there are few fundamental steps in the thin film deposition. I just want to do that. Yeah, explain that. So in the physical vapor deposition, vapor phase generation from a coating material is the first part. That means if I want to suppose if I want to evaporate silver, I need to heat the silver on a filament resistively, so that silver will go to the gaseous phase. That is what. So now that gaseous phase, the transfer of vapor phase from the source to substrate, how you will do? Due to the line of sight. That means that is the vacuum, because when you have a vacuum inside the chamber, the mean free path is very high. It is not necessarily that the entire deposition will be on the substrate alone, but you will have a on the walls of the container also. And the third one is the deposition and growth of the film on the substrate. So what happens when these vapor molecules are condensed on the substrate, and they the layer by layer, when you do the slow rate of evaporation, you will have a layer growth, which ultimately comes the deposition of your thin film. So these are the three fundamental steps involved in the physical vapor deposition, which I am going to discuss in maybe I will introduce a couple of methods in PVD and a couple of methods in CVD also. Okay, this is what happens. So this is enough to introduce thin film. Of course, there are various methods. If you want to qualitative thin film, there are you have to have a pure material, initial material. That is what is the important thing. And so this one I will not discuss. Maybe you can go through the lecture so that you will be able to understand. So now that is a brief introduction to PVD. Then let me also introduce a little bit of a introduction to CVD and a few methods of CVD, and then I'll go to few methods of CVD as well, PVD as well. Okay, so as I told you that CVD, as I told you, everything happens on the substrate. Substrate is the core in the case of CVD. So now when we talk about CVD, there are CVD also, you have a large varieties of molecule methods possible. You can have a low pressure, a high temperature, atmospheric, low, cold wall, hot wall, closed and open. Varieties of CVD methods are possible. First, I want to discuss CVD only, because CVD, it is easy to set up. That is where I am on. I want to discuss first CVD. So what are the types? What is exactly happening in the CVD? These are the three steps I am putting up here. First, what you will do is deliver and meter the reactant and dilute gases into the reactor. That means, suppose if I want to do a silicon deposition, I will start with the gaseous form of the various silicon based volatile components into the reactor. Then what I will do, supply heat to the substrate so that reaction and deposition can proceed efficiently. So what happens? So when I send the volatile gases onto the substrate and heat my substrate, then once the reaction took place on the substrate, what you should do is there are unwanted gases. Byproducts are always there in the case of a PVD, CVD. Why? Because you are talking, you have to decompose the components, and one of the component you will use and other components you don't need. So those waste products, you have to send them off. That is what happens in the third step. So in the case of PVD, what you will do, you will vaporize the material and then bring it to gaseous form and condense it onto the substrate. That is the method core theme, the basics of PVD. In the CVD, what you will do, you will allow the reactant gases into the chamber first. Then you cannot allow the gases just like that, but you have to allow them in a controlled manner and then heat the substrate so that the gases will break into the different components, and those one of the component will deposit onto the substrate. And what are the byproducts are there, and that you will remove. So this is the these are the main fundamental differences between a PVD and CVD. And rest is this is what happens here. This is what I told you in the previous case. I am just putting here. So introduce the reactive gases to the chamber and activate gases. That means to activate gases you need to decompose them. That means either use a heat or a plasma, and then gas absorption by the substrate here, and then reaction takes place on the surface and the film is formed here, this pink form, and then transport the volatile products so outside, and with whatever is the waste you take them up. That is what is the CVD. So in the CVD there you have a different uh, types of APCVD is the atmospheric pressure CVD. What is the basic physics principle in this case is the mass transport limited region. You will have a fast deposition and a poor step coverage. That means the control is less here. And LPCVD is the low pressure CVD here. The reaction surface reaction rate is limited. So here you will have a APCVD mass transport, whereas in LPCVD you have a surface reaction limited. So excellent purity and uniformity because you have a low pressure, but in the top case it is a atmospheric pressure. That's where you will have a difference. Here you will have a low rate of depositions because you are working at a low pressure. You cannot send ingredients much faster into the chamber. That is where you will have a good control here. And then requires vacuum system. As I told you, even if you want to have a pressure, you have to have a vacuum system. So you can have a cold wall reaction chamber or a hot wall, whatever it is. In cold wall, what happens? No reaction on the wall will take place, only on the substrate will take place here. But what happens is that the temperature control will be sometimes will difficult. Hot wall will be particle contamination occurs on the surface. So you have to clean it regularly. That is what happens in the, that is the basic methods in CVD. So LPCVD, as I told you, this is what happens here. So you have a reactant gas that is coming up here, and there are heaters this side here you see, and there is a vapor here. So the reaction takes place here, and then the gas goes out to the out from the chamber. So these are the advantages and disadvantages with the LPCVD. And so as I told you, so you can go through these things with LPCVD. So here, as I told you, one of the good part of LPCVD is faster growth, less auto doping means impurities. Little dilute gas is needed because you are working with a low pressure, and the lower gas consumption also is important, and you will have a fewer byproducts. So if you want to start a chemical vapor deposition, if you can have a rotary pump which costs about 50,000, and a quartz tube about good quartz tube, and a heater will cost you another 25,000. So in 75,000 you will be able to start a thin film deposition method, at least with a CVD and with a good quality, where you will be able to publish a good data and you will be able to do a good product actually. So that is where I started with a CVD initially. Of course, line of sight means depending on your vacuum level it will happen, and poor step coverage also, how much of vacuum is there, based on that you will have that. And another method is the plasma enhanced CVD. What you will do is that instead of, sometimes what happens is everything you cannot heat with a heater. Sometimes you can use the plasma to break the bonds between the molecules. That is what happens here. So you see that the gases are coming inside the chamber here, and what you are doing is the constituents, you are breaking them into different parts, so that with the plasma, so that is that RF signal, you are able to break the bonds. So that way you will have a very qualitative deposition possible. And sometimes what happens is you will not be able to go very high temperatures because some components are very volatile. Sometimes what happens is, even though we can go very high temperatures, but the problem is that your byproducts will be more sometimes. So sometimes we may have to grow amorphous thin films. That means the temperature has to be as low as possible. That way the plasma enhanced CVD method is a very much promising method. So this is all about plasma enhanced CVD. So and then let me move on. And plasma vicinity, what happens is, why plasma is that you can see higher reactivity, can use low temperatures and use low pressure. So that, because if you go high pressure, high rate of depositions, the quality of the film and the control of the growth will be very poor. That is where plasma enhancer CVD is the good part, is important. What is exactly happening in the plasma? That's what I said here. Electrons in plasma, what they do, ionize the gas to keep plasma going on. So the gas, the electrons in the plasma, they will break the ionize, and then they will activate gases by dissociation to enhance the CVD. That means they will break the bonds so that the reaction will takes place. And typically 1% of gas is activated. So that's where you will minimize lot of wastage in the CVD, plasma enhancer CVD. So that is one advantage of it. Of course, I have given some more details. You can work on it. So what are the process parameters in this CVD? Substrate temperature. That means how much of substrate temperature is very much important. If you have a higher substrate temperature, the reaction rate will be faster. So sometimes you may have to have a moderate temperatures. So in that case, you have to grow the film very slowly. Very little heating from a PECVD process. So because that way you will be able to grow film of your choice. And gas flow is one important thing. And as I told you, in CVD, you will definitely have a waste product. So you have to deal with carefully. And the pressure is another important, and the power, because when we are talking about a power, RF power, so there also you can have another control. Okay, so surface area will be whatever surface area you want to deposit in CVD, that much area you will be able to deposit, provided you have the heater under the substrate. Suppose if I want to have a 5-inch disc, the reaction should, I want to have a film on a 5-inch disc. So my heater also has to be 5-inch, so that I will have a thin film deposition entirely on the 5-inch substrate. That is what happens. So you can also do a laser enhanced PVD. That means instead of in the previous case we have used the plasma, so you can use laser also, and these are very sophisticated methods. So when I use a laser, we will have two types of reactions possible. One is called the pyrolytic. What do you mean by pyrolytic? Heats the substrate to enhance the reaction. That means I will send the laser beam to heat my substrate rather than physically heating with a resistive method or some other method. Okay. And then another is the photolytic. That means since laser is a light, you can, with that light itself, you will be able to break the bonds and help the reaction to takes place on the substrate. So either of them you are able to do. So in the pyrolytic case, this is what you are doing here. So laser beam is coming and you are able to break the bonds, and your substrate is here. So heated substrate is here, and your film is forming here. So, and whereas photolytic, what you will do is that you will focus the beam onto the components, and ultimately you will be able to deposit the thin film. So that is what is the LECVD. And MOCVD also is another important thing, and this is very well known. But MOCVD generally we adopt for organometallic sources, source gases. When we have this kind of gases, people use a metal organo CVD. So the best example, we see to deposit gallium, you will use a this kind of initial trimethyl gallium you will start with, and ultimately you will take off a trimethyl outside, and you will only left with a gallium. So that is the advantage here, volatile at relatively low temperatures, because anything organic organometallic components which are very volatile, and they can be broken at lower temperatures. That is what is the important thing. And here the carbon contamination also is there, so that is a small disadvantage, but however you will be able to overcome with that. So that is all about CVD. So what I told you, just let me summarize the CVD. What I told you is that in CVD, I will start with the volatile components and I allow that volatile components to come onto a substrate, where underneath the substrate I have a heater. Because of that thermal heat, the bonds of the volatile components broke, and then you will get a thin film on the substrate. and byproducts are there, you will take them out. That is what is the CVD methodology. And we have seen APCVD, atmospheric pressure CVD, LPCVD, low pressure chemical vapor deposition, plasma enhanced CVD, and laser CVD, and MOCVD, metal organo CVD also. And sometimes what happens is CVD is known for its if you want to grow epitaxial means, suppose I have a molecule A on the first layer. Second layer will be B molecule I want to keep. Exactly on top of A, I want to keep the B molecule, so that the growth will be epitaxial, like you see a column in a building. So you will see that exactly you keep one brick on top of the other, so that that is what is called the epitaxial growth. And that kind of growth is possible with the CVD, because the temperature is one of the important parameter in the CVD. So that's where happens. That is what happens in the case of CVD. So now let me move on to the PVD. As I told you that if I want to start with the PVD, physical vapor deposition method, I have to have a vacuum. Why I need a vacuum? Because see, if I do any reaction in atmosphere, I will have many contamination possible. So we will reduce the contamination, and to create a plasma also, low pressure is good, so that you will be able to send enough reactive gases inside the chamber. That is where the vacuum is very much needed in the case of a PVD. So vacuum deposition is a vacuum part is a must in the case of PVD. So now we will move on to the physical vapor, some of the physical vapor deposition method. Of course, so in the physical vapor deposition method, see, this is what the physical vapor deposition system I have used in the way back 2004 in my laboratory. So what I was doing here, I was depositing aluminum. You see that this is a filament here. On top of it, I have put aluminum, and I am just heating it. So what is evaporation here? Material to be evaporated is heated to increase the vapor pressure. So ultimately what happens, in a reasonably high vacuum, the material atoms fly to the target. That means it will come to the top of it and stick onto the surface. The source material is coated onto the target surface. So what are the steps involved here? So the source material, I start with aluminum, and I make aluminum vapor here. I bring aluminum to gaseous state, and allow that gaseous molecules to fall onto the substrate. Suppose if I want to coat it on a copper plate, I will keep a copper plate on the top, so that the molecules, aluminum molecules will go and sit onto the copper substrate, and then deposit the atoms. So ultimately it will become a solid after some time. So this is what happens in the case of a PVD, and it is very easy, simple method, because whenever we want to fabricate any devices, if you want to have a electrical conductivity or any electrical measurements, you have to have a top electrode. So that way physical vapor deposition is the simplest one. So you can have a different, depending on, if I want to have a powder, I can use this kind of boat. And if I varieties of things are there, you can do in metals, some kind of aluminum, silver, gold, tin, chromium, all this you can do. Some oxides also you will be able to do evaporation. That is what is possible. But in thermal evaporation, there is a problem. There is one problem. What is that problem? When I put my material here, the material will get contaminated with the filament, or the filament, some of the impurities of the filament also may come onto the thin film, so which will contaminate and which will reduce the quality of my film. So to avoid that, we will go for a e-beam evaporation method, electron beam evaporation. There is one more disadvantage in PVD, is that suppose if my melting point of a material is very high, so suppose if I want to evaporate platinum or titanium, which requires, the melting temperature is about 3000 degrees C, which is practically impossible in a physical vapor deposition. So if I want to have a high melting point materials and less contamination of my material in my thin film, then I will go for e-beam. And also that if I want to deposit one layer of aluminum and another layer of TaO2, then another layer of silver or copper or gold, I can in chamber, only I need to do is I just divert the electron beam into that. So that what is exactly happening in the E-beam? So focused beam of electrons are used to locally heat the source. What happened? You see, I have a crucible here, and then underneath that I am having a water cooling, so that at the bottom the crucible will not get heated up, so that there is no reaction between the crucible and the powder, so that you will have only pure material to be deposited, and can be used to heat, evaporate even high melting point materials. That is one example. And if I want to use a alloys, suppose if I want to use a iron platinum, it is a alloy. It is a good magnetic material which is used for a recording, magnetic recording purpose, all that. So how do I do? Iron is a low melting point. Iron, platinum is a high melting point. How do I do? So in that kind of situation, E-beam is the best method. So that is what ideally you suited for a reactive evaporation. Suppose I am using depositing only aluminum. So while evaporating the aluminum, if I send the oxygen gas, I can form a Al2O3 also, aluminum oxide, which is possible in the case of a E-beam. Of course, that same thing can be done in the case of a PVD as well. So that is what happens. What is the advantage here? We see the less contamination from the from source, holder, and a crucible, and we will have a better control over deposition rate. Why so? Because based on my electron beam power, I will, we will be able to controlly grow the thin film. And of course, it is a slightly expensive but a slow rate of deposition, but you will have a very clear, very good quality thin film possible with the E-beam, electron beam evaporation. So this is what happens, summary of that. So there is a cathode filament which will generate the electrons, and these electrons are using the aperture, you will make them as a beam. And if you use a magnetic field, you know that with the magnetic field you will be able to tilt the beam the way you wanted to tilt. You see that here the electron beam is tilted here and guided. So I can have a one more evaporant here, one evaporant here. If required, I can have two more evaporants here, so that I can, if I want to do even multi-layer thin films, it is very much possible with the case of a electron beam evaporation. So another one is called the glow discharge and plasma. So as I told you, plasma enhanced CVD also. Let me clearly discuss about sputtering. What is sputtering? Maybe with a diagram I will explain. You may go through this lecture notes very clearly. I have just mentioned here. I just shown here. So what I am doing is this is the outer layer, the dotted line is my vacuum chamber. So this is my target here. Suppose if I want to have a TaO2 thin film. So this is TaO2. This is my titanium target, suppose I say. And this is my substrate. Here I want to do my titanium atoms to be deposited here. So now how do I do in plasma? How do I create a plasma now? So what I do is, so this is my target, my anode, which is at the negative potential. This is my cathode. And if I apply a potential difference between these two and I allow the argon gas to come inside. So what happens? The electrons which are coming from anode, they will interact with the argon gas that is coming inside, and they get they get ionized. That means argon molecule will become Ar plus 2 electron minus. Probably it is there. So maybe so what happens? You will see the ions coming up, and these ions which are at a positive, they will come towards the titanium target here. So they will take off the titanium molecules and putting onto the substrate. Why they will go obviously to the substrate? Because between these two the pressure is low, so you will have the mean free path is high. So as a result, the substrate the molecules will go onto the substrate. So that is what happens. This is what is called the plasma creation. So what is plasma? You know that where equal number of positive and negative charges are equal. That is what you will see. Okay. So if you see, this is what is plasma. So what happens here? This is what I have just whatever I told you, I'm just putting up here. So you can read these two and you can learn. So let me explain how the plasma coming up here. So this is what I told you. So I have a uh, anode here, my cathode here, anode here. Apply the potential and send a argon gas. Then these argon Ar plus ions will come to a negative potential and they will deliver their momentum and release the target molecules which will fall onto the substrate. This is what is the plasma. So here this is what exactly practically what is happening. So you see here in this case what is happening, these red ones are the Ar plus ions. So they are giving their momentum to the, so this is my target. Suppose if I say this is my titanium target, what happens? These red ones are Ar plus ions. They are coming and when they are hitting, they are removing some of the molecules, which are titanium molecules, which will deposit onto the substrate. That is what is the plasma. So you see here on the substrate, you see the yellow ones are the titanium molecules which are coming and falling. And you see that this is the background where the ions are created and the plasma is continuously happening. Of course, looking at this, suppose if I have a metal, I do a DC sputtering. That means I can use a direct current source. So I can use a plasma, the DC source, and use, because the molecules, the metals will have a low bondings, so bonding strength, so that that energy, few electron volts of energy is sufficient to release the molecules from the metal target. But if I have an insulator, which is called the insulator, what happens is the bonding is very high. You need a very high energy to remove a molecule, one atom from the surface. So in that case, the DC source will not work and we will use a RF signal. So when we use a DC source, we call it as a DC sputtering. When I use a RF source, I will RF power source, then I will call it as a RF sputtering. And then there is one more point I just want to mention here. Suppose this is my titanium, but I want to have a titanium oxide film onto my substrate. What I will do? So what I will do is during the deposition process, I will allow the gas, oxygen gas, to flow into my chamber. So that what happens? The titanium will, the molecules which are highly reactive, they will immediately react with the oxygen and try to form a TaO2 onto the substrate. So that you will call it as a. So now what happens? If I use a DC sputtering, I will call as a that process is as a DC reactive sputtering. Why I am saying reactive here? Because I am allowing my metal molecules to interact with the oxygen. So that is what, as a result, you will get a oxide layer. So that is what is called the DC reactive sputtering. If I am using RF sputtering, I will call it as a RF reactive sputtering. Of course, there is one more thing that I just want to mention here. Suppose if I want to have a very high rate of deposition, suppose I say that in 5 minutes I want to have 1 micron deposition. Sometimes the deposition will be very slow here in PVD, because you will have a atom by atom. This is atomic deposition. You see these yellow molecules are atoms which are falling onto the substrate. So it will take time to deposit a thin film. So now to increase the ionization process, what we will do is we go underneath the cathode, I will place a magnet here. So what is the purpose of magnet here? Magnet will attract the electrons. So magnetic field will allow the electrons to confine around the cathode. As a result, what happens? If the electrons are more confined at the cathode, then what happens? You will see the more ionization coming. If the more ionization is coming, then you will have a high rate of deposition. So that is called the magnetron sputtering. So if I can have a DC reactive magnetron sputtering, I can have a RF reactive magnetron sputtering, or RF magnetron reactive sputtering, or DC magnetron reactive sputtering. So this is what happens in the case of a sputtering. I hope I have conveyed you the sputtering and PVD and say electron beam evaporation. So if you see what is the difference between evaporation and sputtering, here you will do a thermal evaporation, here you will do the ion bombardment. That means there is a momentum transfer of argon ions to the target. So that is what is called the momentum transfer or ion bombardment. So you see here directional evaporation according to the cosine law. That means the deposition comes up here. Here also have the cosine law, but a high sputter rates possible here. Here, multi-component will be slightly different, but you'll be able to do that in the case of a sputtering. Availability of high evaporation sources, purities are possible, but in the case of people say that purity is less, no, you can still have a better purity possible. But in the case of evaporation, there is a contamination that is possible, but which is not there. If your sputter target is pure, in the case of sputtering, you will be able to do a very well. So in this case, you will see that the gas phase you will see and the condensed phase. So all these three steps of evaporation PVD I am just mentioning. First you are making them vapor species and then you bring them to gaseous phase. So and then you make them to condense onto the substrate. So here condensing atoms have a relatively low energy, but in the sputtering you have a high energy. As a result, it will result in a good crystallinity of the thin film. So here low gas incorporation occurs because there might not be much gases here, but some gas molecules may be incorporated in the thin film, but which will not anyway affect your growth of your thin film, because if argon atom is embedded in your thin film, suppose anyway it is a inert molecule, it will not affect. But if there is oxygen, anyway oxygen is there in your film also, there is no problem. So here the grain size is larger, but here also you can have larger, but sometimes in general it will grow smaller. So the good adhesion, that means the film attaching to the substrate is very good here, but which is not good in the case of evaporation. So here few grain orientations are possible. Here you will have a many grain orientation possible in the case of a sputtering. That is what. So to put up simply, this is what happens here. In evaporation, you have very low energy atoms, but in the sputtering, you have high energy atoms. Here you have a high vacuum path, that means mean free path is high, but here mean free path is low because you are introducing reactive gases into the chamber. You have a large grain size here, but you will have a small grain size in the sputtering. You have fewer grain orientations because the rate of deposition is very slow, but in the case of sputtering, it is very high. That is where you have many orientations. So adhesion, that is sticking of the film to the substrate, is poor here, but it is very good in the case of a sputtering. So, and I will move on to the parameters. So if I use a target power, what is happening, all that, probably you can just look at these things. I don't have much time. And later, as I told you, ion beam sputtering. In the case of sputtering, what happens? We are creating the ion beam in the between the electrodes. In the case of ion beam sputtering, what we will do? We will create the ions in the source itself using the Kaufman source. And see, this is my target. Ion beams are directly coming. In the case of sputtering, you will not be able to see the ion beams, but in the case of ion beam sputtering, you will be able to see. And this is your target. Of course, this is a very specialized technique, and you can see the rest of the details with the ion beam sputtering as well. And another technique is called the molecular beam epitaxy. This is a important, very classic deposition method where you want to have a very precise controlled growth. For example, let me show you the example here. This is a very high vacuum chamber where the pressure inside the chamber will be 10 power minus 12, at least of that order. And you see that what happens is that in the molecular beam epitaxy, I have a aluminum, copper, and magnesium. You see that you will have a precise control growth in the MBE. See, you see that first layer I want to have a copper. So I have a copper atoms. And then I want to have a magnesium atoms to sit on the copper atoms. Then I want aluminum atoms to sit on. So you will be able to grow one top of the other nicely. So that is what is called the epitaxy. So you will be able to grow exactly, or between the copper atoms, if I want to have one aluminum atom, I can also have this. That is possible in the molecular beam epitaxy technique. So which is a very sophisticated technique and used for very precise control devices. And another one is the pulse laser deposition method or laser ablation. Why I am saying pulse laser deposition? Suppose I have a material called YBA2Cu3O7. That is a superconducting, high temperature superconducting material that is available so far. Now, so this is 1237 component called. Suppose, if there is a slight deficiency in oxygen, it will not behave as a superconductor, rather it will behave as an insulator. So where the stoichiometry is very crucial in the case of this component. So if whenever the stoichiometry is very crucial, in that context, you will go for the pulse laser deposition or the laser ablation. That means I want exactly 1 yttrium atom, 2 barium atoms, 3 copper atoms, and 7 oxygen molecules. If there is a slight deficiency of oxygen, this material will not behave like a superconductor. But what is the laser going to do here? So what is laser is going to do is that a high power excimer laser is focused on the target. So your laser beam is coming, which is focused onto the target. This is your target here. The target is ablated to form a plumes of atoms, molecules, and chunks. You see, it will come and hit on the surface, and it is forming a plume. That means what it will do is it will melt the top layer of the material, and which will try to bring this material to sit onto the substrate. It will not decompose the material. It will take a small chunk, small piece of surface layer of the target and bring it here. But the sputtering, what you are doing, you are completely bringing the every molecule, every metal or metal oxide into the molecular form and bringing onto the substrate again. But in the case of PLD, pulse laser ablation, what are you doing here? You are not bringing them to individual evapors, but you are taking a surface of a target, this one, you are putting onto the substrate. That is what is the advantage. Where you want to go for a complex deposition method, materials, then PLD, pulse laser deposition or laser ablation is the important, crucial. So what is the advantage here? Advantage of PLD is that the complex materials can be easily ablated, easily. And the challenge is that minimizing the chunks. That means if you use very high power, it will you will see the you will not have a smooth surface, rather you will have the rough surface possible. So that is what, if I want to summarize, whatever we have discussed, for example, thermal evaporation, E-beam, sputtering, PEDC, PECVD, LPCVD, I have just given the details. The whatever I have spoken for the last 1 hour is summarized in this substrate, in this slide. You can just understand very simply. So let me go. So let me discuss about uniformity, purity, and the cost. Maybe rest you can maybe substrate temperature you can see. So thermal evaporation, as I told, uniformity is slightly poor, impurity is high. Why? Because it may come from the source. And here also uniformity, E-beam also slightly poor, but impurity is low. You don't have much impurity, but the cost wise is slightly higher. Sputtering is you can use both metals and oxides possible. Uniformity is excellent here, very good here, and impurity is also low. And you will see, if you want to have a small grains, it is very good. You directly deposit nanomaterials here, and film density also very good, and you will see that the cost is slightly higher also. Okay, and the PECVD is you can use for dielectrics. Here uniformity is good, impurity low here, and film density also good, but the cost was also very high. LPCVD also same. So you have to decide. There are vast varieties of techniques possible. Of course, I have mentioned only few of them. There are vast number of techniques are available. But before I go for choose any deposition method, first I need to choose what I need to choose is that what is my requirement. then accordingly choose your deposition techniques. So this is what I have just summarized again, and this is all about your different thin film methods that are possible. And regarding the characterization, I will not be able to fully talk about characterization techniques, but I will give you a brief summary of a characterization so that you will be able to, based on this, you will be able to choose whichever characterization you need. Let me go to the characterization techniques also. Okay. So now why we are going to do earlier, if you look at in the physics point of view and most of the characterizations, we will only use to do a traditional characterizations like conductivity, all that. But now now we are having a microelectronics or nanoelectronics where you have to have a very precise um, control over the properties, and you should have a complete information of the film, and that is the reason we have to have a very precise characterization tools important. So that is what, let me go through this slide. In advancement of science and technology, the discovery of novel materials, that means thin film, all the thin films are novel in the nature. Why? Because novel in their nature, because you have modified the surface. The surface to volume ratio is very high. Now the material will not behave as its bulk, but it will exhibit an enormous enhancement in its properties. In that case, you have to have a proper tools to characterize them. Otherwise, thin films people have been depositing right from beginning of the 19th century. But why we could not have this many smart devices at that time? Because we don't have tools to characterize them. That is the reason we were late. Now, due to this advancement of the technology, we have to be very precise understanding the properties of the material. So we will see some of them. So this is what I want to do summary so that we will be able to understand. Suppose what do you want to know and how do we find out? This is what I will give a summary. These are the guidelines. I am not going to the details characterization techniques, but suppose what do you want to know and what are the equipments required. That is what. Suppose if you want to know how the sample look like, how the film surface of the film look like. Suppose if you have a large particles, if you have a very thick film, you can go to optical microscope. Suppose if your grain size is a 2 micron, you can go to optical microscope. But if your grain size is a micron size or a nanometer size, then you go with the SCM or transmission electron microscopy or a scanning probe microscopy. So microscopic scale and atomic scale. So if you want to look at if your film is about a atomic scale, very thin film, then you go to the scanning probe. Or if it is a slightly thick, maybe 100 nanometers, 150 nanometers, you can go with the transmission. If your film thickness is about 200 nanometers, you can safely go with the scanning electron microscope to understand. Because why we want to know how the surface looks like. Surface is one of the important in thin film. The basic important part is the surface, because that is where you have a large surface to volume ratio available. So it is important that whether I have a triangular particles or spherical particles or square particles, whatever those things, if you want to know, you have to go with the microscope. That is all about if you want to know about the sample looks like. But if you want to know the structure of the sample, that means what is its crystal structure, whether it is in the cubic phase or monoclinic phase, then what you will do, if you want to know the structure of the sample and you want to know internal structure, density, microscopic and atomic scores at atomic scales, then you go with the X-ray diffraction, where you will be able, if your film is crystalline, then you will be able to know that yeah, what is your crystal structure. And if you want to know the thickness, at the same time you will be able to know the stylus profilometer, and also you will be able to know the continuity of the film also. Again, ellipsometry you will understand, and lead and read to understand the patterns of the information about the structure of the sample. So that is what required. And if I want to know what is the sample made of, suppose I have started with I have shown you in the case of PLD YBA2CE3O7. Now if only one yttrium atom is there or two yttrium atoms are there, barium is in barium is 2 atoms are there or only 1 atom is there? 3 copper atoms are there or not? 7 oxygen molecules are there or not? How do I know? If I want to know the composition, I have started with the same composition, but in the thin film, whether all the elements are present or not, I don't know. So to know that, we will go for a elemental composition. So to go with the elemental composition, you will go with the agar electron spectroscopy, where you will see from the core of the element, each element has its own fingerprint. So in agar electron spectroscopy, RBS and secondary and mass spectrometry, what you will see, you will be able to see the elements and its composition, magnitude, how much of element is there. And we all of us know IDAX, which is attached to SCM. You will know that. And XPS. Suppose I have a iron in my sample. So whether iron is in a 2+ state or 3+ state, how do I know? So to find out whether my iron remains in the +2 state or a +3 state, what I will do, we will go with the XPS, X-ray photo electron spectroscopy. And also that impurities. Suppose I have started with a YBA2C3O7, but in the process there is some impurity, like some magnesium ions, magnesium molecules, maybe some impurity might be there. So I want to know whether what is the impurity level, magnitude of the impurity level. So that way I will go with the XPS also. We will know that what is the impurity level possible. All that based on the binding energies will be able to know. So and we will with RBS will be able to also know the thickness of the film also. Even IDAX we will not be able to know. In IDAX we will be able to know the elemental composition, provided if it is a slightly thicker film. And then next will, if I want to know the optical properties, then we can see that these are the things that we see. If I want to know the refractive index, what is my refractive index possible? And if I want to know absorption coefficient or the thing, I will know, I will go to ellipsometry. Dielectric properties also we can measure in ellipsometry. Otherwise, in general, dielectric properties comes in the bottom. So, or I can take a transmittance spectrum, or rather than the absorption spectrum, you can take a transmittance spectrum. Why transmittance spectrum is possible in the case of oxides? Because these are the transparent layers. You will be able to easily get a transmittance, and from that you will be able to get a band gap, absorption edge, dielectric properties, refractive index as a function of wavelength. You will be able to get it. So what are the if I want to know the electrical properties of my sample, my film, what I will do? So in order to do the electrical properties, I have to have a capacitor structure. That means I have to have a bottom electrode in between my insulating electrode, oxide layer, and again top electrode, so that I'll be able to understand capacitance, conductance, resistance, and everything I'll be able to measure as a function of frequency, as a function of temperature, so that when I use the device for a particular applications, whether if my temperature goes higher side, whether this device is stable or not, I'll be able to find out. And if I am using a magnetic material, so I will take a hysteresis loop, or measure electro-optical Kerr effect, Mach effect, or a ferromagnetic resonance in FMR, so or VSM, or PPMS. If I am using a magnetic material, so these are the characterization tools possible, where you will be able to measure, and also that from that you will be able to know that what kind of material I'm using, whether I'm using a ferromagnetic or a ferrimagnetic, antiferromagnetic, or diamagnetic, paramagnetic, I'll be able to find out. And if I want to know the mechanical properties of the sample, internal stress between the substrate and film, it is very much important. And friction and adhesion, we will go for stress curve measurements to see what is the internal stress between the film and the substrate, and whether the film is sticky properly or not. We will be doing the adhesion tests, and friction tests also we will do to see that how much friction it can withstand. So these are the, so if I want to know these are the parameters. If I want to know, these are the characterization tools possible, so that we can go to that particular instrument and get the information. Okay, so one second, this is hanging. Yeah, so now if I want to know the general fundamentals of characterization, generally what are the tools available for characterization fundamentals? Light tools like electromagnetic radiation, like UV visible spectrum, or you can use electrons, in XPS, and ions, nuclei, or protons. Used to probe these are the probes, available probes, to understand the nature of the materials, thin films we use, and neutrons, neutral atoms. So now touching the samples, the van der Waals forces, or that is what you see if you go with the AFM, you will see you will play with the van der Waals forces and between the tip and the substrate to get the microstructure of the film. That is what happens. So now you will see that if your sample can withstand high energy electrons, then what are you going to do here? Backscattered and secondary electrons. That is what you do in the scanning electron microscopy. So mostly you will use secondary electrons to get a clear picture, but backscattered electrons comes from your sample. Sometimes if you want to have a sample information, you will use a backscattered image. So similarly, whatever techniques I have put up earlier, I am putting there the detection, what are the detection mechanisms, and what information, what is the energy and which technique. That is what I am putting up here. If you have if your film can withstand a moderate energy, sometimes all the films cannot withstand a 30 keV energy. So that way you go the moderate technique. That is what is the Agar electron spectroscopy. What is the main tool that you detect is the secondary electrons. So if you want to go with the light energy here, so it is a X-rays. So again you have a secondary electrons to find out the chemical composition and state of the particular element. You will see the X-ray XPS. And if you have low energy, if your sample only will be able to take 100 electron volts, then you will use the diffraction as a principle. That is where you use a lead. And if you want to have a moderate, then you will go with the read. So that's what. If you have a moderately high energy possible, then you will use the secondary ions. That is what is called the SIMS. If you are using a polarized light, then you will use the polarized light, and that is what is the method you use in ellipsometry. So these are the techniques. So now in general, there are two types of characterization techniques. One is called the counting techniques. That means suppose if you see XRD, you will see 2 theta versus intensity. That means those are the number of photons that are reaching your detector. So it is intensity, force, number of particles, polarization, and that is where we call them counting techniques. Some of them are, when you go to the spectroscopy techniques, what are that? You will the distribution by energy, wavelength, mass, and position. So we need to choose which one is I am using. So that, see, any light techniques or light based techniques are very sensitive. So if you want to have a very sensitive measurements, better go with that. That is what you have to come across. So because I don't know the need of yours, that's the reason I am giving a very generalized thing, so that based on this information, you will be able to choose your characterization tools. So now, but why we are doing a thin films? Maybe in a couple of maybe in 5 minutes time, I will try to close here. What is the difference here? Because you are what is the difference between surface and bulk properties? Why thin film technology is very important is that at the surface we are dealing with the 5 to 10 atomic layers. That is the difference between bulk and thin film. As a result, the properties are very different. So what happens? Why? Due to the large surface to volume ratio, the properties of the material increases. These are the reasons why the bonding and mechanical properties are different. Why? Surface atoms have no bonds, because in thin film you just have a 5 to 10 atomic layers, so the atoms are not bonded to each other properly. So as a result, they are free to move. The moment I subject with a particular tool, they give a enormous response. That is what is the um, advantage in thin films. We can get a can get a surface reconstructions. That means my surface can be modified if I give a high energy tool. That means the arrangement of atoms is possible. So again, electrons bounce off the surface as well as off from the other atoms, because they are not properly bonded. Electrons travel tens and hundreds of angstroms before scattering of an atom. So if close to surface, many scatter sooner from surface. So that is what changes electrical properties at the surface very high. That is where these thin films will behave differently from bulk. And the chemistry is different at the surface. Atoms from bulk may segregate to surface to minimize the free energy. Sorry. Atoms may segregate to the surface to minimize free energy, and impurities from outside environment also comes off, so that the combination of them will work in favor of enhancing the properties. So that is what makes the difference. So that is where the surface of the thin film and bulk properties are totally different, and as a result you will have the enhanced properties. So I think with that I am done, because I have many things to talk about. I think this is good enough whatever I want to give. So I am open to if you have any questions on that. Thank you.
Shainita,
Yes, sir.
can you please, a lot of questions are there, I see. Thank you very much, Dr. Pamu. It was fantastic talk. Actually, you covered almost all the things. And even now, I want to develop a PVD with the help of you. Thank you very much. So now I will hand over over to Shainita for the questions.
Sir, our first question today is, can we synthesis pegylated nanoparticles using LPCVD method, polyethylene glycol?
Definitely. See, what size you wanted, all that is an important thing. For every CVD method or for every particular method, you have to optimize. I have told you some processing parameters. If you can play with them, it is it's possible to grow a controlled particle sizes. It is possible.
How can we calculate the thickness and surface area of the thin film?
Yeah, so thickness is see, if I am using a transparent substrate, I can take a transparent spectrum. From that, I can calculate thickness. Or if I am using a PVD or thermal evaporation, for example, there is a thickness monitor inside your chamber itself. So that, while depositing the thin film itself, if you give a input of your material, density and other parameters, you can see the thickness while depositing the thin film itself. Or there is a surface profiler. With that, you will be able to measure.
If we have to deposit thin film on fabric, which method is suitable? Hello. If we have to deposit thin film on fabric, which method is suitable for this?
Shainita,
Yes, sir.
after completion of your question, say over to Pamu and mute your mic.
Okay, sir. Now my third question is, if we have to deposit thin film on fabric, which method is suitable? Over to Pamu, sir.
Yeah, somehow, madam, I didn't hear. So his audio is not visible to us.
Are you able to listen, sir?
Yeah, yeah,
I think he muted himself. I'm calling him.
No, sir. He's actually shows in green, not muted, but somehow he's not talking. Could be some audio, I'm not sure, but his mic shows in green color to us. Dr. Pamugar, can you able to hear, sir?
Sir, Pamu sir did not muted anything. Can you do anything, Viru sir? Pamu sir is like unable to listen the questions.
Yeah, but there is no issue from our side, sir. I think Pamus are some settings or something like. Since we are
then.
fine, we can able to
shall
hear each
I
other.
ask him to join once again? Is it possible, Viru garu?
Yeah. He can join once again. Or he can able to just mute and unmute by himself, and he can get it corrected.
Could you please? Yeah, you do that, sir, once.
1 second, sir.
Are you able to listen me, sir?
No, I can't able to hear him. But other participants and you and me and Chainita, everybody we can able to hear.
Okay. Okay
I
then.
think Thomas are left.
Yeah, left, and he will join. He is joining.
Yeah,
we'll keep 1 or 2 minutes in the time, because however we have another 10 minutes time is there for next talk.
Yeah.
In the meantime, dear participants, very good. A lot of questions you are posting here. It's very interesting to see the questions. Even the questions are, most of the questions are very interesting. In the meantime, if anyone can raise your hand so that you can give your feedback about this talk orally. So please, in the chat box, if you type your name, so that the technical persons can give you a choice to talk in the session. Please, if someone in the chat box.
1 second, sir. Let me log into my another system to unmute. 1 second.
Okay. Yeah.
Brijesh Patel is raised hand. I can unmute him, sir. 1 second.
You can unmute him, Brijesh Patel.
Yeah. I'm going to do that. I think I did. 1 second, sir. 1 second.
Hello, Brijesh Patel. Hello, Mr. Brijesh Patel.
Yeah, I unmuted Brijesh Patel. Can you talk, Brijesh ji? Hello. Yeah, Brijesh ji, please go ahead. Sir, somehow I could not able to talk. I don't know why.
Someone else?
Can I go to Manasa?
Yeah, she raised her hand, sir.
Yeah. Manasa, can you just have your word?
Yeah, Manasa, could you please speak a little louder? Manasa, DJ?
I'm not sure. They raised a hand, but even after we unmuting, they're not. Shall I go to Kalpana ji next one?
Yes, sir, please.
She went. Arasavalli Naga. Next person is Arasavalli Naga. I think she raised her hand.
Hello?
Yeah, we could listen your voice very clearly, Nagamalli, Arasavalli Nagamalli. Hello.
Ellipsometry we are using now, sir. Hello?
Yeah, please.
Sir, regarding the thickness measurement of any thin film or thick film, ellipsometry can we use, sir?
Yes, you can use it. That is one way of calculating thickness.
Yeah. Sir, I have one more doubt, sir. Myself, I am a research scholar doing metal oxide semiconductor gas and fabrication, sir, under INUP project, IAS Bangalore. Sir, here we have a results extracted from XRD, sir. Hello.
Yeah,
Hello?
please go ahead. Please go ahead.
Sir, through XRD, 4 results came, that is Y calibrated values, Y observed value, and Bragg's value, and difference value. Difference value.
Okay.
So, from these number of values are extracted for my nano composite powder. So, how many graphs that I can extract from these 3,000, more than 3,000 data values obtained, sir? How many, what are the various characteristics that I can extract from this XRD data?
Okay.
Can
It's
you
like
please suggest me,
yeah,
sir?
yeah. Pamu sir is not here as of now, but I can answer your question actually. So you can first of all you have to see the JCPDS data card. You have to fix the Miller indices. You can find out the crystal structure. You can find out the crystallite size, and then you can measure the lattice imperfections. You can measure the structure factor. You can measure the if you use Ritfield analysis, then you can use for other applications also. But however, if you are looking, even you can use Millman-Hawkes equation, one more equation, to find out the average crystallite size also. If you want all these things, you just I can share you one paper with you all, and you can read that paper and you can do the calculations.
This Miller indices HKL from the obtained data, sir. Why obtained values?
Exactly. And I will share you in the group one paper how to calculate X-ray data and other things. Okay, research article.
Yeah, I visited CNST 2015 summer program, sir.
Okay, nice.
Yeah, Ashok sir is there now. You have allotted Ashok sir as a one of the research scholar. He allotted me and he guided me so many things during those 1 week day program we have attended.
Thank you, Ali. Thank you very much. I will share you the data to you. Please give a chance to others. Okay, thank you.
With whom, sir? Shall we go to Shanti ji?
Yes, sir. In the meantime, Professor Pradeep Paik joined, sir. Just check it out, sir. He told that he will join at 11:25.
1 second, let me check. Pradeep, no, sir. He is not joined.
Okay.
Maybe you can send a message, sir. Maybe.
I am calling him, sir. I am calling him. In the meantime, you can give rather than questions. If anyone gives the feedback, that may be a good idea. You just ask them, sir. In the meantime.
Okay, sure. Anita, so who is the next person? Shanti Ganapa, do you have any questions?
Yes, sir. Yes, sir.
Please, madam. Shanti Ganapa.
Yes, sir. Namaste, sir.
Namaste.
Sir, I have a question. If we synthesize a thin film by using an Acilar technique, then the range, then the thickness of that thin film ranges below the 100 nanometers, sir. So, sir, how can we measure this thickness of the thin film which is synthesized by using an Acilar method, sir?
I'm very sorry. This question, I don't know. I cannot answer. I don't know basically this question. Pamu sir is the best person. Okay. If you please post this question in the chat box once again, I will give. Sir, actually, did you post the question in the chat box?
Yes, sir. But okay. I got okay, 2 of them answers, sir.
No worries. I will share all the questions to Pamu sir, and before today evening, all the questions may get the answer. Thank you very much.
Yes, thank you, sir.
Then shall we go with Pandurangarao garu?
Yeah, please. Yes, sir. Please, sir.
Pandrangara garu, just can you have your
Sir,
question, please?
did you join, sir? One minute. Viru garu,
Yes, sir.
Dr. Pradeep Payak is unable to join due to some reasons. What is the reason? Like what is the mail ID you used for him to set up the thing, sir?
1 second, sir. You can forward the attendee mail, then I can make him presenter right away without asking any details.
Okay, you need exact mail ID, whatever he is using. Am I right, sir?
Currently, I cannot able to answer because since the meeting is started. So the quick option is you have the attendee login link. You send it to him. He can log in as an attendee. I can make him a presenter right away.
Okay, sir. Okay.
Do you have that one, or do you want me to send that attendee link? 1 second, I will share with you, sir. Yes, sir.
He's telling link is problem, something he's telling. What shall I do?
Sir, I sent you one attendee link. Ask him to just use this link and join. I forwarded one link, sir. Just forward this to him, sir. Mallikarjun Swami, sir told he will send research paper. Please share in the group. Also, it will be beneficial. Yeah, I think sir will share. Please wait for some time.
Sir, he is facing a problem, sir. Viru, sir. Pradeep Payak is facing a problem. I don't know.
1 second, sir. Give me his mobile number to me. I will call him and resolve right away.
Okay, sir. I'll do that, sir. I'm sharing the mobile number of Professor Pradeep Payak.
Yes, please. Yes, please.
Dear participants, Professor Pradeep Payak from IIT Varanasi will be joining soon. Please bear with us. Shainita, any instructions need to be given to the participants or delegates? Any questions which we need to answer in the, like people are asking regarding the certificate or any other things? Can we answer that questions in the meantime?
Yes, sir, we can answer.
General questions are like you will be given the certificates by within 2 days after the completion of the workshop. That is one thing. E-certificates will be provided to all the participants, those who are registered and those who are giving regularly feedback. This is one thing.
And please make sure that you give your name spelling properly. The same will be given on your certificate. So make sure that you provide correct spelling of your name, department, and organization.
Yeah. Yeah, research paper. Yeah, I will share it in the group.
Feedback form will be given only on that particular day. So before this feedback form will not be given on the next day. So make sure that you present daily and feedback regularly at that particular time. Two feedback forms will be given every day. That is, for every session, there will be one feedback form. So you have to fill both the feedback forms.
One more information. We will be having a session on Friday, 28th at 2:30. So, Shainita, could you please create a link for Friday's webinar, Friday afternoon talk, a small Google link who is trying to attend, so that based on the number of participants, we can request Professor Subramaniam from IIT Hyderabad to deliver his talk. So you create one small link, those who want to attend on Friday afternoon talk of Professor Subramaniam Garu. Can you do that, Sainita?
Sure, sir, I'll do it.
Yeah. Maybe by today evening, if you can send that registration link, maybe it will be useful. Whether we need to conduct it or not, we can decide. Based on that, we will do.
Sure, sir, I will be doing it.
Yeah. Sorry for the inconvenience. Generally, I want to see the timings will be very perfect. Due to some technical issues, we were waiting actually. We'll just see what happens.
Venkateshwar Garu Pack is having some internet issue and he is resolving. Maybe he will be back in 2-3 minutes, sir.
Yeah, very. Then I will take the today's talk, sir. I will talk. Viru Garu.
Yeah, let me make you the presenter, sir, now. Quick.
Yeah.
Yeah, you should be having some screen sharing up.
Yes, sir. Yes, I'll do it, sir. Within 1 minute, I'll do, sir.
Sir, you can share your screen, sir. Venkateshwar Garu.
Yes, sir. I am doing it, sir. Just 1 minute, sir. Yes, I am doing it, sir.
Yeah, please, sir.
Are you able to see my screen, sir?
Yes, sir. You can maximize in the presentation mode and it should be good to go, sir.
Yeah.
Great. Yeah, please carry on, sir.
Yeah, very good morning. I'm very sorry for the problem which was happened now. That's the reason now onwards we will check it out based on that. So now I will be talking with you all nanostructures sensors. So this is my broad area of research, nanostructures. And if time permits, I will also talk about glucose sensing. I don't think so. I'll be talking today glucose sensing. I'll be talking specially on sensors, gas sensors, and nanostructures, how the nanostructures and gas sensors plays important role. So if you take the nanoparticles, it's if you see the size of the particles, nanoparticles, there are n number of interesting applications, starting with textile, biomedical, healthcare, food and agriculture, industry, electronics, environment, and renewable energy. So you can wonder what type of applications these nanoparticles will be having, especially if you consider textiles. Textile is like a technical textile. The meaning of technical textiles is like you can use textiles for air purification, textiles for current production, that is capacitive kind of textile, supercapacitor applications, medical textiles, and then there are like anti-strain textiles, self-cleaning textiles, electroconducting textiles. Like that, there are n number of applications in the area of textiles. Coming to the biomedical, you may be wondering there are interesting area of applications, starting with drug delivery to cancer therapy, and then especially this is the one area where people are working very effective manner, imaging of cells. As on today, if you see a patient get cancer, generally he need to go to hospital. After that, they do generally PET scan. PET scan is the scan where you can see a single single day cancer cell also. But the problem is we don't know what type of proteins were there in that particular cell, protein cancer lump. So imaging, by using the imaging, you can do n number of applications like surface enhanced Raman spectroscopy, MRI, and there are n number of imaging technologies are coming up. So based on quantum dots as gold nanoparticles, silver nanoparticles, there are different types of nanoparticles where size-based color modifications will happen. So such kind of nanoparticles could be used in imaging, drug delivery, hypothermic treatment, biomarkers. This is another area people were working in effective manner, molecular tagging, biomarkers. These things are not only diagnosis, but also treatment could be happened in the process of diagnosis itself. It's like a therapeutics. It's a combination of treatment as well as diagnosis. These are the things which are having a lot of potential applications with the nanoparticles. Healthcare, I was like trying to tell you, there are n number of antioxidants, sunscreens, fungicides, there are n number of things. Food and agriculture is the one area where people are working a lot. Food packaging to food sensors. There are n number of food sensors are coming up with the help of this type of nanomaterials. And then and it could be used even now, as on today people are working on seed germination, faster growing of seeds, and then nano pesticides could be used, or rather using a lot of more amounts of cages of pesticides. People are trying to do that kind of things, and industrially as well. Electronics, I need not even talk. And then coming to renewable energy, this is one area where people are exploring. The first talk was that actually people are trying to work on hydrogen storage, and there are n number of things which are coming up. So if I say what are the advantages of smallness, if you it's a simple example. I'll ask you, if you have a sugar powder and sugar cubes, which one will mix very fast? You can simply say that sugar powder will mix very fast. The reason is smaller. Smaller means quicker to connect. Quicker to connect means more reactive. Then you may ask a question, why only milli technology? Why only nanotechnology? We did not study the milli, that is 10 to the power of -3 and 10 to the power of -6 micro technology. And what made us to do interesting thing, well, like nanotechnology, why we are very fascinated towards the nanotechnology, why not milli and micro? That is the one point we need to very clearly understand before you are going to talk about the nanomaterials and applications. So if you take the smallness gives a lot of property modifications. If you take color modification will happen in the case of gold. You know very well the color of gold. I need not tell what is the color of gold, because you know very well what is the color. But if I reduce the size of gold to 50 nanometers, and then it will become brick red, and then it will become blue, and then it will become white in color. So like a water kind of things. So what is that? What is that is happening here? Physically, the color modification is happening when you are reducing the size of the gold nanoparticles. So color modification, melting point, the physical points, what I mean to say, physical properties, the strength of the materials, the conductivity of the material, not only conductivity and resistivity and other electrical properties. So I can broadly say physical and chemical properties are going to be modified when you reduce the size of the nanomaterial. Reactivity, and then all these are the properties which are going to be modified. So depending on your application, we need to tailor the materials as per our convenience, as per our requirements. So here, the basic point, what I want to tell you here, the smallness. The smallness makes things better. So before I'm going into smallness, first of all, we need to understand why only nano? Why not 10 to the power of -3 meters and 10 to the power of -6 meters is is not showing anything great. That is the reason I was trying to tell you, milli and micro technologies, we did not much worried, but we just jumped into nanotechnology. So as an example, let me take a simple example to solve this problem. Consider 100 nanometer diameter particle, a particle whose diameter is in the range of 100 nanometer, which is also in the spherical form. Then you know very well, formula for spherical volume is equal to 4 by 3 pi r cube. So because I gave diameter, I substituted the diameter and I calculated volume, that is 5.24 into 10 to the power of 20 minus 23 meter cube. And similarly, I also want to calculate the surface area. Surface area is 4 pi r square. The formula for sphere is 4 pi r square, and then pi d square is the, if I convert into d, and then I calculated the surface area, that is 3.141 into 10 to the power of minus 14 meters square. It is the surface area, and this one is volume. And now, if I measure surface to volume ratio, if I measure surface to volume ratio, then surprisingly, it will be greater than 10 to the power of 7. You try to understand this point. In the similar way, if I take 100 meters, if I take 100 meters, and if I substitute here, you know very well, just it is 100 cube. And here also it will be 100 square. So approximately, if you find out the surface to volume ratio, it will not be more than, it will not be 10 to the power of plus 7. It will be very, very small difference will be there. I think you understood very clearly. I am repeating it once again. The scale matters, the smallness matters. When you are taking 100 nanometers and try to determine volume and surface, and if you find out surface to volume ratio, because it is 10 to the power of minus 27 is there at the bottom, and on the surface 10 to the power of minus 14, then you will get plus 10 to the power of 7, which is surface to volume ratio is, the meaning of that is surface to volume ratio is increasing enormously. That is happening in the case of nano, which will not happen in the case of meters, milli and micro. It will happen in the milli and micro, but not this much predominantly. So here, the basic takeaway, is surface to volume ratio is increases, and hence the percentage of atoms at the surface force becomes more dominant. This is the point we need to understand very clearly when you are dealing with nanomaterials. Generally, accepted materials properties are derived from the bulk, whereas percentage of atoms and surface is a minimum. That is what I am trying to explain you. In another manner, take another simple example. Even you can calculate this also. Take a cube whose length, breadth, and size, and then you find out once again surface to volume ratio. You will wonder once again, the surface to volume ratio will be predominantly increasing in the range of nano. I will put it in another form. Is like this. If I am going into cutting into pieces, 1 centimeter cube, made 1 centimeter cube, then it will cover almost all football ground. The meaning of that, I want to try to tell you that the surface to volume ratio is going to be enormously increases in the case of nano, whereas in the case of other things, it is not that much. Another simple way to understand that, don't worry about quantum confinement and all other new things. Let me take a simple example. Based on the quantum confinement calculations, what I'm trying to do is on x-axis, this is the size of the particles in the range of nanometer. You see, in the range of nanometer. 1 nanometer, 10 nanometers, 100 nanometers, 10 to the power of 3 nanometers, 1000 nanometers. Like that I am going. So what do you mean here? This is nothing but millimeter. This is nothing but micrometer. So when on the y-axis, surface to volume ratio. On the y-axis, I am having surface to volume ratio. On the x-axis, I am using size of the particle. See here, at after 100 nanometers, there is a predominant increase. There is an increase in the peak is happening. Are you seeing it very clearly? That means after 100 nanometers, there is a modification in the surface to volume ratio. There might be here, see here, in the range of milli, in the range of micro, the surface to volume ratio remains same. That means on the x-axis, the curve is same. But whereas in the case of 100 nanometers, after 100 nanometers, in between 100 to 1 nanometer, this is happening. What is that? Is there is a increase in the surface to volume ratio, which is a great thing people found, and that is what the definition of nano is. If the size of the materials or in any dimensions is below 100 nanometers, then we call them as a nano size, nanoparticles, or we can say that is a nanomaterial. We will say that is a nanomaterial. This is the first takeaway I want to give you in the talk. What is that I am trying to tell you? In the case of milli and micro, there is no improvement in the surface to volume ratio. Whereas in the case of size, in the case